Sunlight is the basis of all life on Earth. By driving photosynthesis, it enables plants to produce the oxygen animals breathe and directly or indirectly the food they eat. But there's more to light than meets the eye. For millions of years, insects and plants have conducted a liaison that is invisible to humans. They communicate by means of a form of light that we can't see. There is another form of energy somewhere between light and heat, which very few animals can sense. With special equipment, we can see both forms of energy, looking into a world that is all around us every day, but has been invisible until now. Watching ants with a heat-sensitive camera is yet another way of seeing the invisible. The flowers that gladden our eyes with their warm pink color don't look pink to the wasps, bees, and hoverflies that are feeding on their nectar. These glowing red trumpets are striking, but they're red only to our eyes. To a butterfly, they advertise their rich nectar content on a different wavelength. Butterflies can see ultraviolet light, beyond the range of our limited vision. Change the light by boosting the ultraviolet and see what happens to the appearance of what we think is a red flower. Most nectar-producing flowers bear ultraviolet signposts, guiding pollinating insects to the nectar with which the flower pays them for their services. Some don't. As the light changes, some flowers fail to reflect the ultraviolet and remain their old color. All these flowers have three different identities, one in white light, one in boosted ultraviolet, and another in ultraviolet alone. A flower called Rudbeckia reflects ultraviolet all over its petals, so that to an insect it looks like a white star surrounding the source of nectar and pollen. But when the center of a flower is dark already, the insects can find their food and pollinate the flower without further help. Other flowers, which are very similar to Rudbeckia to our eyes, look quite different to an insect. Perhaps a silvery disc, like a target whose bullseye is a feast. Most insects cannot distinguish the color red. Just as our vision runs out at wavelengths above violet, theirs stops short of red. A poinsettia attracts birds with this pattern, but insects with this. The camera sees it as a pale purple, but we can have no idea of what an insect sees. Perhaps it's this. There's no way of finding out until the bees talk to us instead of we to them. We can only watch the interplay between insects, birds, and flowers and wonder. Watching a sulfur butterfly on a Gaillardia flower reveals something new. The butterfly also reflects ultraviolet light. The orange-gold pattern of the flower is transformed by ultraviolet into blue, or a mixture of cream and pink, depending on the strength of the light source. What happens to the colors of the butterfly? Watch. On a female butterfly, the faint spots on the hind wings are delicately outlined in silver. But the trick really works on the male. He gives the species its full name, the orange-barred sulfur. As a male emerges from his chrysalis, the orange bars on his forewings are already visible through the transparent pupal case. But when the wings emerge into the ultraviolet light, the orange bars are revealed as shining silver, strongly reflective, like a mirror. Flashing the ultraviolet light reveals how brightly they shine. As the male expands his wings, the mirrors become larger and brighter. Plainly, they're going to be important to the butterfly at some stage of his life. A closer look at the female shows that it's not only her rings that reflect ultraviolet. There's a pattern on her fore and hind wings quite different from her plain yellow dress in white light. These are the marks by which male and female recognize each other, using ultraviolet reflections to distinguish members of their own kind from other species around about them. When the adults are flying free and the breeding season is underway, the marks are what enable them to mate with their own kind. A dummy butterfly without the marks is interesting to the exploring males, but when it fails to respond to their own flashing wing mirrors, they soon lose interest. A female orange-barred sulfur responds at once, and mating can take place. Other species use the same system of signaling, but with their own distinctive patterns. Knowing that insects cannot see red, it's odd that so many of the visible wing patterns contain red. But color has other functions, such as camouflage or warning. As the wings tilt in the sunlight, they reveal patterns that were not visible before. The ultraviolet vision of butterflies is not infallible. It can be outwitted by one particular predator. A yellow black-eyed Susan flower has its own ultraviolet pattern to attract butterflies. Only the petals are reflective. The stamens remain dull, of little interest to the butterfly. This flower does not have two sets of stamens. It has a crab spider sitting on it. In white light, the spider is perfectly camouflaged to match the color of the flower to protect it from predation by birds. In ultraviolet, it seems conspicuous, but because it doesn't move, the butterfly doesn't notice it. Crab spiders eat butterflies. Like that. If flowers and insects have enjoyed a long liaison, spiders and insects have shared millions of years of predation. The wiles of the spiders are a match for the strategies and agility of the insects. Even the dragonfly, a master flyer, must fall occasionally into the trap. But a dragonfly is about as big a victim as even a large spider can handle. If anything bigger flew into the web, it would mean problems for the spider repairing the damage. Even something as small as a hummingbird is too large to eat. They often visit spiders' webs to collect silk to use in their nests. It is in the spider's interests if the web is clearly visible to birds, so that they can avoid it. Ignoring ultraviolet signals, which it cannot see, the hummingbird seeks out flowers by their color and by the quantity of nectar which it has learnt they contain. Other nectar-eating birds do the same. Meanwhile, the trees around them are festooned with webs which would impede their progress, if not kill them. But they don't get caught. They can see the webs. The spider has made sure of that. Below the center of these large, strong webs, there is a structure called a stabilimentum. People used to think that it stabilized the web in the wind. But it's a flag to make the web conspicuous. The sticky strands, which would catch small birds, are shiny to make the web even easier for them to see. Insects, on the other hand, for all their remarkable vision, do not see on that scale. For them, the web, flag and all, is too big to notice. A dragonfly is the most agile of all flying insects, but it can't escape a web it can't see. Some spiders make their stabilimentum even more obvious by decorating it with the trussed and drained corpses of their prey. But there is more to life than what we can see, more than meets the eye, in fact. Somewhere between the senses of feeling and seeing lies a borderline level of energy too subtle to feel and too dim to see, until now. It's heat, but in very delicate gradations. Using a new type of camera, we can now see it. This camera has revealed a great deal of information about a large number of animals. Take the brown wood ant, for example. At sunrise, a wood ant's nest is deserted on the surface. the ants are all underground sleeping. But as the sun rises above the trees, they begin to emerge. Speeded up film helps to show the increase in numbers of ants on the surface as the day warms up. At normal speed, the ants seem less frenetic. In fact, they look positively lethargic as they wander about on the surface of the nest, some climbing up among the pine needles and some scrambling back down into the depths. They don't appear to know whether they're coming or going. Some of them just seem to lie there. Far from being models of industry, these ants look as if they're on holiday. The answer to the idle behavior of these workers lies under the ground in the depths of the nest. There in the brood chamber sits the queen, laying the eggs which will hatch into a new generation of workers. But the brood chamber is cold. This is how the heat camera sees it, turning temperature into color. Purple and blue are cold colors, and red and yellow, grading to white, are warm. The inside of the nest is at about 19 degrees centigrade, and the sunlit surface at about 26 degrees. The ants coming down are a warm white with red edges. After a few minutes in the chilly interior, their images turn green as they cool down. New arrivals are glowing with warmth from their sunbathing on the surface. Blue with cold, the first sunbathers make their way back into the light and warmth of the forest floor. Far from idling their time away in the morning, the workers are using their bodies to collect heat to keep the colony alive. And so it goes on until the little mobile storage heaters have carried the warmth of the morning from the sunshine into the cool gloom of the nest, raising the temperature of the brood chamber until the queen can begin her day's laying. And there is the queen, a giant female, now at working temperature, with her courtiers around her bringing food and tending to the eggs she lays. The mystery of the wood ant's morning behavior had been worked out in theory some time ago by devoted scientists using thermometers and watching the ants' comings and goings. Thanks to the heat camera, this is the first time it's been seen. Another natural mystery involving heat concerns the humble bumblebee. The heat camera can show the answer to that too. The question is, how can bumblebees start their foraging and nesting so early in the year when it's too cold for most other insects to fly? The answer is that they have an inbuilt source of heat, like a tiny chemical furnace where they can burn fat until their muscles are warm enough to work. This too had been suspected for a long time, but with the heat camera it finally became visible. After crawling out of its hole, the bee stands still and switches on the central heating. The small white area in the thorax represents the hottest part of the bee's body, where its flight muscles are. As the warmth spreads, the bee becomes more active and finally flies off. The interactions between insects and plants are double-sided. Each benefits the other in what is known as symbiosis, literally living together. In return for the insect's services in transferring pollen from one flower to another, the plant pays with nectar and pollen for the insect to eat. Once the bumblebee's body temperature has been boosted by its internal heater, the fuel from the flowers is sufficient to keep it going while daylight lasts. The glorious complexity of a passion flower offers a perfect target and landing place for pollinating butterflies. Patterns like this, reinforced by ultraviolet signals, advertise a very high-value fuel for the insects. By watching butterflies through a heat camera, we can see how quickly the nectar provides energy, giving off heat as it is oxidized inside the butterfly's body. The warm red glow of the thorax and abdomen contrasts with the cool greens and blues of the wings. The heat camera and the ultraviolet camera have combined to give a new insight into the everyday, transforming mundane events into wonders by extending our senses until they reach into the invisible. Insects live in a very ancient world, led by evolution along paths that have been closed to us, until our own evolution led us to invent the means of exploring them.
There's a full-colour survival guide to all the programmes in the current series, containing information on the animals and habitats featured. If you'd like a copy, send a self-addressed label and cheque or postal order for £1.50, payable to Anglia Television, to Survival, Anglia Television,